Today we'll talk about function M file. We will learn how to write our own function M file. We will learn the boring part, basic rules for creating functions and handling them, then how to call out for sub-function within the main function, and something cool called function handlers. How would we handle function within function in our M file or in our code? And eventually we will learn how to debug an M file. Again, we had previous exercises how to debug an M file, but we will talk in more details how to be more systematic in debugging your code. Now, we talked before about Newton's method. Mathematically, Newton's method is a way that use the computer power to get as close as possible to the root of the equation. And if you remember, we already did a similar example, or probably the same example, on how to solve equations with Newton's method. Now, here we have a function mathematically equal x to the power 3 plus x minus 3. And we can think that we want to solve the equation x to the power 3 plus x minus 3 equals 0. Now, we will create the first M file for us. We will say function of y equals f of x. You can start to, in your editor, not in your command line, create function y equals f of x. Then in the second line, y equals this equation, x to the power 3 plus x minus 3 semicolon. After you save that as f.m, then we can move to the next one. The next one is basically the derivative of the function x to the power 3 plus x minus 3. So we create another file in another editor file. Yeah, you can save that as f.m. Then go to a new editor space for a function that we call df.m, which is the derivative of f. If you don't know derivation, it's the opposite of integration, where we take x to the power 3 would be 3x squared plus 1 as the derivation of x to the power 3 plus x minus 3. So we'd say function y equals df of x. So we're saying y is the derivative of the function f of x. We call it df of x. And y would equal 3 multiplied by x to the power of 2 plus 1, then semicolon. And that's another script that we save it as df.m. So you got now f, then you had df, and you had the Newton. So either you want to do it on your computer or not. The whole point is you create a function f and the derivative of f in another function, and you call it as a separate script. Now you can call these two within your long script. So you can see here, regardless of how Newton method works, here you have x minus f. So you call this guy f of x divided by df of x, and you continue your code. So you called these two codes that are separate from your code, and you use them as a backup within your process. If you execute it, you should be able to get either, he should find the 0, because it's an iteration method. He's going to find either a solution, 0 solution for you, or he's going to tell you 0 not found. So he's basically going to ask you, what is your initial guess? And based on that, he's going to try to find the nearest 0 solution. 0 means the crossing of the x or the y axis as a solution for the equation. So if I run it here, let's see what we get. When I first wrote it, I wrote it on a PC, on a Windows-based computer. Then I copied it on the Mac. On the Windows-based, he used to give me solution. Now, when I do it, I'm not sure if he's going to give me, probably not. Okay, so he said 0 found at 0.1213. So as you can see in the yellow marks, so that's your f of x. So you called y function, you open with function equal y equal f of x. And what's in the y? What's the f of x in this case? This. Then you said y in another script called df of x. And what in the y is the derivative of f of x. Then you called them back here, f of x divided by df of x. Whatever initial value you plug in as an x, He took it and executed the code to give you the final result. That's the whole idea we're trying to deliver here. Basic rules. The general form of a function in MATLAB. Firstly, your function M file would be whatever name you chose, .m, and it has the following general form. You start with the word function, then you have the outer argument 1, outer argument 2, in that case we had function y, one argument, equals, then you have name of the inner argument 1, inner argument 2. You can include as much as you want, and of course you can have comments, commenting out and following the process. One fun fact, well, let's continue on this. Then you have the out argument 1, out argument 2, and so on. Just keep in mind that you had function y equals 1, 2, 3, equals f of x, basically. Then you said f of x equals x cubed plus 2x plus 1, and so on. So that was your outer argument here. Then your y was outer argument here. Then you had the name that you got to call for that exact function in this case. Now he's telling you here, comment to be displayed with help. Now there is an option while calling out different functions. Like when you call out df of x, if you call df of x with help, then he's gonna show you what is the function df of x does. Then he's gonna tell you if you are commenting out in df of x over here, if you commented out here like, oh, this is derivative of function x or function f of x, then he's gonna bring down with the new code, with the new script, he's gonna bring down your comments from the previous script. Now the function keyword, function file must start, of course, with the keyword function in specific. Now how to handle input and output arguments or inner and outer arguments. The input and output arguments are considered just as a dummy variable, and they just help to define the function means of communication with the workspace, so that MATLAB will know what kind of function you're calling within that function without any confusion. Now, if you have multiple output arguments, if you have more than one output argument, the output argument must be separated by comma and enclosed in square brackets in the function definition line. So multiple output arguments, if you have, in this case, we had one argument. If you have more than one argument, you get open brackets, argument 1, comma, argument 2, and so on. Naming convention for functions, you know that. Function names must follow the MATLAB rules for variable names. If the file name and the function definition line name are different, then the internal name in this case would be ignored. Now that's what I mentioned as help text. When you type help, then after that function name, in this case df of x, then MATLAB will display your comment lines that will appear between the function definition line and the first non-commented or executed line. Local variables or scope, any variable defined inside a function is inaccessible outside that function. Those variables are called local variables, where you can't access them. They exist only inside your function, which has its own separate workspace from the base workspace of the variable defined in the command window. Global variables, you can always declare global variables by writing the word global, like in this case, global Planck, whatever he did here. So he identified as global variable. There's no local variable in this case. So it doesn't matter if you have script 1, script 2, script 3. If you identify a certain variable as a global variable, you can use it across the scripts without any concerns. Now there's persistent variables. Those variables called persistent, if the local variables normally need to exist within the function, persistent variables remain in existence between the function calls. Persistent means a variable that you see it basically inconsistency everywhere in the code. Persistent variable initialized to the empty array. Again, the important rules here, we're gonna have examples on it. The rules that I think good to know, but doesn't really matter. We just move forward with it. Now we have here an example for persistent variable called count. we use it to count how many times the function test is called. So now you start with identifying function test. Now you have persistent count. If is empty, open parentheses, count, then count equal 1. Else count equals count plus 1, then you end. In this case, persistent variables remain in the memory until the M file is cleared or changed as using clear test. Let's try together this persistent variables. Okay, let's run it. Okay, that's cleared the situation. All right, let's go back. Now, vector argument. The input and output arguments may be vectors. As we can see, function d equals dice of n. D equals floor of 6 multiplied by the random numbers 1 to n plus 1. How function arguments are passed? If function changed the value of any of its input arguments, the change wouldn't reflect in the actual input argument on return to the workspace unless the function is called with the same input and output arguments. Input arguments appear to be passed by value. Now, for the simulated pass by reference, function is called with the same actual input and output arguments. As we can see in the example here, function of y equals prone of x, y equals x to the x not to equal 0 as the logic argument over here. That will remove all the 0 elements from its input argument. Okay, we'll move forward. Sometimes while writing the code, you have too many arguments. You don't know how many arguments being presented under y, under x, under z, and so on. You can always use the function nargin or nargin or nargout, so you will know how many inner or outer arguments that you are using for that exact variable. For the subfunction, function M file contain the code for more than one function. That happens a lot. The first function in a file is considered the primary function. So now when you wrote your Newt-gen or Newton code, the first one, then he called 2 other scripts. The Newton code was the primary code, and the other 2 are considered as subfunctions. Now, you can see those functions in the primary function. They'll be visible, but each subfunction will begin with his own function definition line, and subfunctions would follow each other in any order after the primary function. So going back to our code, so you defined f, defined df, then you called both in Newton over here. So Newton is your primary code, where he called those 2 codes and executed them within. Maybe if you go to f and execute it alone, nothing would happen or you get an error, and same for df. But when you execute them in Newton, MATLAB could be able to see the big picture, what's within this and what's within this, to be able to execute the whole code. For private function is a function where he lives in a subdirectory with the name private. Private functions are visible only to functions in the parent directory, and I wouldn't honestly ask you about it, but it's good to know. Now, the pseudocode or pseudocode, the Pcode files, the first time a function is called during a MATLAB session, it is executed or compiled or parsed into pseudocode and stored in the memory to obviate so that it will be ready whenever you ask for it. Then it will be executed again during the current session. Now the pseudocode remains in memory until you clear it with the word or the function clear. Then after that, you write the function name. You can use the Pcode function to save the compiled version of M file so that you can use it later in another MATLAB session, or by using by other users who want to hide their algorithm. So you can say Pcode stats, that will execute stats.m and will store the resulting pseudocode in the file name stat.p. I can't tell of any useful application for this kind of feature, which is the Pcode. It's basically you're hiding your code output in a different file, which is called, in this case, stat.p, or whatever code name that you choose. Now, the fun part, function handles. Now, go ahead on your MATLAB and write fhandle equals @sqrt. So there's two functions here, function called fhandle and function called feval. Here it's an easy application for the function handles, and I can see hundreds of applications for that. Now what you're saying here, fhandle equals sqrt. You are telling MATLAB, let the word fhandle always be as if I type in sqrt in MATLAB. Then the feval is kind of the tool where to use the fhandle. So you write feval, open parentheses, fhandle 9. Now what is fhandle? It's the square root of whatever after the comma. So fhandle of 9 will give you, the square root of 9 will give you back 3. And if you say feval fhandle 25, it's going to give you back the square root of 25, which is 5. Go ahead and try it, but you just write here fhandle, then equal sign at anything else, not necessarily sqrt. You can write maybe x to the power of 2, and every time you plug in a number, you're gonna make that number multiply by himself or by 2, or to the power of 2. There's many functions and many applications that you can use this situation in it, and could be very helpful for you. Handle equals @sqrt. So now the word fhandle acts as the square root. Then you would say feval, open parentheses, fhandle, comma. Now fhandle, we know it's the square root. We can say 64, close parentheses. And if you run it, he should give you back the square root of 64. Now the function duality, that's telling you there is sometimes two ways to write the same function and get the same results. As we can see here, axis off, that you remember as you're drawing or plotting x and y, you don't want to show the axis, then you can say axis off, but you can write it as well as axis open parentheses, then you have off between quotations, then you close parentheses. Same thing for display, as I'm showing you here. You can say disp high between parentheses and between quotations, and it's going to give you back high. And you can display high directly, and he's going to give you back high. And that's the main concept of function duality. There is sometimes many ways to write the function and his components, and you still get back the same output result. Now, debugging an M file. Let's go back to our Newton script. Let's try to learn together how to debug an M file. Now you have this function, and you don't know, at a certain point there is an error. Of course, thankfully, MATLAB will tell you in the command window which line does the MATLAB have a problem. But sometimes you don't have really a coding problem. Your MATLAB executes and he gives you output results, but the output is not the one you want. Maybe you're solving a physical problem. Maybe you're solving an equation or mathematical problem. Then the result that you get by doing by hand is different than what MATLAB gets you, and you know you did something wrong along the way. You're going to trace that and see what's going on. Now let's say here at steps equals 0, we have an issue. We're going to stop the code when I run it. I want it to stop here. What I do, you can see here, as long as you're an editor, you have here the number of lines being listed on the left. You can choose the point where you want to have your code execution to break, and you click on it. In this way, the code gonna stop executing until he reach here. And of course, your workspace will always update and pause based on the way you split down the code. Let's say this first section, I want to make sure what are my workspace values. Then the next stop, I want it to be at steps equals steps plus 1. Then I can mark number 10. This way, I will pause execution at line 10. That's one way to do it. Let's go ahead and do that and try to execute the code and see how it is looking. Section break is just exactly as you're clicking on a certain point, but you choose whatever section before the point you choose, that's where you stop the execution, I believe. So if you hit section break here, you see he split this, whatever before and after the point you choose are kind of two sections. So now we have either we chose which step we're gonna stop, or of course, using the step run, which you make the run step by step, or use a section break. How about if we do section break one more time and say run section instead of run? So section break, then let's say we want to run this section. He already highlighted in blue. Run section. Okay, let's run section. Starting from here. Now, okay, yeah, initial guess in the first section, that's right. Now 12. And nothing happened. So the first section executed. You're gonna run the next section and see what happens. Now there you go, you can get your answer by running the next section. Now there's something called recursion or recursion. Some mathematical functions are defined recursively, which means in terms of simpler cases of themselves. What does that mean? If we have factorial function in MATLAB, we know that when you have 9 factorial, that's 9 by 8, by 7, by 6, by 5, by 4, by 3, by 2, by 1. The general form of factorial is the exclamation mark. When you have n with exclamation, 5 with exclamation, that means factorial of 5 or factorial of n. In mathematics, the general form equals n by n minus 1 exclamation. As long as one exclamation is defined as 1, MATLAB will help the function to call himself. And this process is called recursion. What does that mean? So if we make a code here called fact.m, we defined a function y equals the factorial of n. So we're defining the recursive definition of n as a factorial. Now another way to calculate the factorial, if n greater than 1, y would equal n by the factorial of n minus 1, else y would equal 1 and you end. So let's try to write and test a function called double of x, which would double the input argument. So the statement x equal double of x should double the value in x.